Hello, welcome back to our discussion on nuclear chemistry. Specifically for this episode, we'll talk about the types of nuclear reaction. Earlier in our previous episode, we discussed about the nuclear stability. We have learned that for smaller nuclei, which has atomic number equal or less than 20, this stable nuclear has a neutron to proton ratio close to 1:1 are said to be stable. But as the nuclei get larger, it takes a greater number of neutrons to stabilize the nucleus. Okay, why do we have to stabilize the nucleus? Because a stable nucleus that not emits any particle. But an stable nucleus will emit a particle, and this will depend on their position, the nuclear position, with respect to the belt of stability. When the nuclei that is above the belt of stability, they have more here if we refer to the band of stability as we have discussed in the previous discussion. When the nuclei falls above this belt of stability, that means they have too many neutrons compared to the protons. For example, a element 20 having 40 neutrons, it is above. Or having 30 neutrons, it's above the belt of stability. When the nuclei falls below the belt of stability, that means it has too many protons compared to neutrons. And they tend to become stable by emitting positron or electron capture. On the other hand, the nuclei that falls above the belt of stability, which has more neutron than proton, tends to convert the neutron to proton, thus emitting beta particle. We have learned likewise that there are no stable nuclei with an atomic number greater than 83. And this nuclei whose atomic number is greater than 83 tends to decay by alpha emission. Okay, in this episode, we'll learn the different types of nuclear reaction aside from radioactive decay. Okay, the radioactivity is the spontaneous decay or disintegration of unstable atomic nucleus, which is accompanied by the emission of ionizing radiation such as electron, proton, and neutron. Radioactive substances that occur in nature emit alpha, beta, and gamma rays. We have two types of radioactivity. A natural radioactivity that exists in nature. It belongs to any existing radioactive families or series. Examples of these are uranium, actinium, and thorium. On the other hand, artificial radioactivity is these are produced by man. Example is actinium, astatine, and francium. Okay, there are four types of processes that involve nuclear transformation. One is radioactive decay, which emit particle. The nucleus emit particles such as alpha, beta, gamma, or a positron, or it can capture an electron. The next is nuclear transmutation. We will discuss the detail of all of this later. And we have nuclear fission and nuclear fusion. Radioactive decay is a process in which the nucleus decays spontaneously, giving off an energetic particle. It is a change that takes place in the nucleus of an atom to make it stable. The more stable nuclei resulting from the radioactive decay is called progeny or daughter nuclei. We have five modes of radioactive decay. The first one is alpha decay. This is a type of radioactivity in which the alpha particles are ejected by the nuclide. Alpha particle contains two protons and two neutrons that are lightly bound together. For example, here we have a plutonium-239 emits an alpha particle when it decays. What new elements is formed? So we have learned from balancing nuclear reaction that the mass number must be conserved by adding the mass number on the reactant must be equal to the sum of the mass number in the product. And likewise, the atomic number must also be conserved, or the charge must be conserved. The charges on the reactant side must be equal to the charges on the product. Okay. So in this case, we identify X. So we have 94 as the atomic number of plutonium, where when an alpha particle is emitted by plutonium-239, therefore this element X is 92. Okay, with 92 plus 2 is 94. Then 239 minus 4, that is 235. So if you refer to your periodic table, the element number 92 is your uranium. So X is a uranium with a mass number of 235. Okay. So plutonium-239, when emits alpha ray, the daughter nuclei is uranium-235. The next radioactive decay is called a beta decay. A radioactive process is classified as beta decay if the atomic number of the nuclide changes but the mass number does not change. Example, here we have a beta decay of sodium-26. What new element is formed? Again, applying the knowledge that you have gained in the previous episode, we balance the mass number and the atomic number, or the charges, both product and reactant. So if we have sodium with atomic number 11, meaning that is the charge, positive charge, and emitting a beta particle here, undergoing a beta decay, so this must be element 12. 12 minus 1 is 11. And since the mass of beta is 0, so we have the same mass as of sodium. Again, referring to your periodic table, element 12 is magnesium. So therefore, sodium-26 undergoing beta decay, the daughter nuclei is magnesium-26. In this process, electron is ejected from the nucleus. And in the process, a neutron is converted into a proton. You will see here for sodium-26, the number of proton is 11. The number of neutron is 15. Okay, so there are more neutron than proton, and therefore it is, if that is so, it is above the belt of stability. So sodium 11 with 15, so it's above the belt of stability. Okay, where at this lower portion, it should be 1:1. Okay, so it tends to emit beta particle to convert the neutron to proton. Okay, so when the sodium-26 emit a beta particle, the daughter nuclide, magnesium-26, the number of neutron is 14 and the proton is 12. Okay, so one of the neutron is converted to proton, and the ratio of neutron to proton is lower. Okay, and the neutron to proton ratio decreases since the number of neutron decreases and the number of proton increases. Okay, we can illustrate it here. The number of neutron to proton ratio, that is 15 to 11. That is 1.36:1. In this case, for the daughter nuclei, that is 14:12, it becomes 1.17:1. Okay. This daughter nuclei can further emit beta particle so that the ratio of neutron to proton will decrease. Nuclides that have too high neutron-proton ratio, poor stability therefore decays by beta emission. And these are the points representing nuclei of this type lie above the belt of stability or to the left of the zone of stability here. So nuclei that lies above here on the above the belt of stability tends to emit beta particle as we have discussed in the previous episode. Okay, moving on, the third example of radioactive decay is a positron emission. In a positron emission, this is a process in which a positron, which is a positive electron, is injected from the nucleus. And in the process, a proton is converted into a neutron. So a proton is converted to a neutron, okay, emitting a positive beta particle or called a positron. A K captured or electron captured is a process through which the neutron-proton ratio of an stable or a proton-rich nuclide may be increased. In this process, the nucleus captured an orbital electron. Okay, if we recall your atomic structure in your general chem, okay, you have the nucleus and the energy level is referred as KLMN. The first energy level is referred as K and the second LMN. It is the electron in the K energy level that is being captured by the nucleus or by a proton. Okay? So, in this process, the nucleus captured an orbital electron from the inner energy level, which is the K energy level. The captured electron converts a nuclear proton into a neutron. The transformation results in a product nucleus with one less proton and one more neutron. Okay, so a proton captured a K electron and the proton is converted to a neutron. 1 plus -1 is 0 and 1 plus 0 is 1, which is the charge of neutron 0 and the mass of 1. Next, we have gamma emission. A gamma emission is an emission from an excited nucleus of a gamma photon with a wavelength of 10 to the negative 12 meter. Often, gamma emission occurs very quickly after a radioactive decay. However, in some cases, an excited state has a significant lifetime before it emits a gamma photon. Gamma has no mass and no charge. Thus, it causes no change in mass, neither on the atomic number. Gamma rays almost always accompany alpha and beta radiation. However, since there is no effect on the mass number and atomic number, they are usually emitted from the nuclear equation. The next type of nuclear reaction is the nuclear transmutation. This is a process in which one nucleus is transformed into another through the bombardment of various subatomic particles or ions. Nuclear transformation differs from radioactive decay in that the former is brought about by the collision of two particles. Here we have an example of a nuclear transmutation where nitrogen-14 is bombardment by an alpha ray producing a product nucleus, which is oxygen-17, and a particle, or proton. A nuclear transmutation can be abbreviated as you write the reactant, isotopes, and you enclose the particle in a parenthesis. The first particle that is written is the particle in the reactant. And we have the particle in the product, close parenthesis, and we write the isotope in the product. Okay, another example is when iron 56 is bombarded by deuterium. The product is manganese 54 and an alpha particle. Again, this nuclear transmutation can be abbreviated by writing first the symbol of the isotope in the reactant, that is iron 56. Then we have in parentheses, we write the particle in the reactant, which is the bombarding particle. Then the second symbol in the parentheses, which is alpha, is the particle that is emitted as a result of nuclear transmutation. And the second isotope or symbol after the parentheses is the product isotope, which is manganese 54. The D means deuterium, an alpha particle, or it could be replaced by the helium atom with a mass of 4 and a charge of positive 2. Now, the third type of nuclear reaction is nuclear fission. This is a process in which a heavy nucleus is split into lighter ones, generating one or more free neutrons. Because heavy nucleus is less stable than its product, this process releases a large amount of energy. We'll discuss in detail later, and we will quantify this large amount of energy later in the future episode. The first nuclear fission reaction studies was that of uranium-235. When uranium-235 is bombarded by a neutron, it produces a nuclei of krypton-95 and barium-138 and 3 neutron particles. The significant feature of uranium-235 fission is that more neutrons are produced than are originally captured in the process. This property makes possible a nuclear chain reaction, which is a self-sustaining sequence of nuclear fission reaction. In less than a second, the reaction can become uncontrollable, liberating a tremendous amount of heat to the surrounding. With just one neutron bombarding the nucleus of a uranium-235, you produce 3 neutron particles as one of the product. And this can be used in a succeeding sequence of nuclear fissions. Since it's less than a second, the reaction can become uncontrollable, liberating a tremendous amount of heat to the surrounding. The disadvantage of nuclear fissions is the disposal of its nuclear waste. In nuclear fission, this is a process in which 2 light nuclei combine to form a heavier one. If 2 light nuclei combine or fuse together to form a larger and more stable nucleus, an appreciable amount of energy will be released in the process. And the nuclear fission is largely exempt from the waste disposal problem like in the nuclear fission. Example of nuclear fission are the following reaction, where you have deuterium and tritium producing an helium nucleus and neutron. Or you have 3 helium combining with 3 helium producing 4 helium and 2 proton particle. Or 2 proton combining to produce deuterium and a positive beta particle or a positron. Since in nuclear fusion, the combining small nuclei into larger ones is largely exempt from the waste disposal problem, so there are ongoing researches into the harnessing of the nuclear fusion for the production of energy. The nuclear fusion occurs constantly in the sun. The sun is made up mostly of hydrogen and helium. In its interior, where temperature reaches about 15 million degrees Celsius. Because a fusion reaction takes place only at a very high temperature, they're often called thermonuclear reaction. A major concern in choosing the proper nuclear fusion process for energy production is the temperature necessary to carry out the process. Although thermal pollution would be a problem in fusion has several advantages. One is the fuel are cheap and almost inexhaustible. And two, the process produces little radioactive waste. If fusion machine were turned off, it would not shut down completely and instantly without any danger of meltdown. Now you may ask, if fusion is so great, why isn't it there were even one fusion reactor producing energy? The basic problem is finding a way to hold the nuclear together long enough and at an appropriate temperature for fusion to occur. At temperature at about 100 million degrees Celsius, molecules cannot exist and most or all of the atoms are stripped off of their electrode. And you have learned in your general chemistry, this is the state where the gaseous mixture of positive ions and electron is present, which is called the plasma, the state of matter called plasma. The problem of containing this plasma is formidable one. Okay, what solid container can exist at such high temperature? There is none unless the amount of plasma is small, but when the solid surface would immediately cool the sample and quench the fusion reaction. One approach to solving this problem is to use magnetic confinement. Because a plasma consists of a charged particle moving at a high speed, a magnetic field will exert force on it. And another promising design employs high-power laser to initiate the fusion reaction. However, like magnetic confinement approach, laser fusion presents a number of technical difficulties that still need to be overcome before it can be put to practical use on a large scale. Okay, moving on the types of nuclear reaction, let us have example. For part A, we are asked to complete the preparation of some transuranium elements. These are elements with atomic number greater than 92 and classify also the reaction as radioactive decay, nuclear transmutation, nuclear fusion, or nuclear fission. Okay, for the first example, we have here uranium being bombarded by a neutron. Okay. So when uranium is bombarded by a neutron, producing more neutron, automatically that could be nuclear fission. Nuclear fission. Okay. So to complete that, we have here 92 minus 51. That will give you 41. So element with atomic number 41. Element 41 is nubium. And for the mass number, 235 plus 1, that is 236 minus 132 plus 3 here. 135. So 236 minus 135. That is 101. So we have nubium 101. 101 plus 3, 104. Okay, that would give you 104 plus 132 would give you 236. Okay. For the next reaction, we have here Neptunium 239 emitting a beta particle. Again, since a beta is emitted, that is radioactive decay. Okay. To balance that, that must be element 94 because 94 minus 1 is 93. And element 94 is plutonium. If you refer to your periodic table. Okay. So to add the mass, 239. Okay, minus 0, that is 239. So the product nuclei is plutonium-239. And that is radioactive decay emitting a beta particle. For number 3, we have on the reactant side. On the reactant side, we have lead-208 and a known particle here. And on the product side, we have hafnium-245 and neutron particle. Again, if we balance the charges, we have 108 plus 0, 108, and we have only 82 here. So if we deduct 108 minus 82, that gives you a mass number of atomic number to give you atomic number 26. Okay, element 26 is iron. Okay, from your periodic table, iron is 26. Iron 26. Okay, then we continue. We balance the mass number. We have 246 here because 245 plus 1. Okay, minus 208. That gives you 38. So you have iron 38. Okay, so these are a fission of two small nuclei producing a larger nuclei. So this is a nuclear fusion. You fuse two small nuclei. The next we have curium 242 or 242, curium 242. And we have a unknown particle in the reactant. The product is californium 245. Okay, the total charge is 98. 98 plus 0, and we have 96 here, so there must be a charge of 2 here. Then we have 245 plus 1, 246 minus 242, that is a mass of 4. So it must be an alpha or helium particle atom with charge of 2 and a mass of 4. Again, there are 2 particles here, one on the reactant and one on the product. So this is a nuclear transmutation. Again, we have learned a while ago that the difference between nuclear transmutation and radioactive decay. Okay, the nucleus is emitting a particle, whereas here the nucleus in the reactant is bombarded by a particle and producing a new nuclide and a particle also. So there are collisions of two particles, one at the reactant and one at the product. Okay, for the last example on this part, we have californium 249, and we have here a reactant, an unknown reactant, which we'll try to find out by balancing the reaction. The product is boron 263 and 4 neutron particle. Okay. Since the neutron particle is neutral, so we can just balance here in terms of atomic number. So we have 106 minus 98. So this particle has a charge of 8, the unknown particle. Then next we balance the mass number. On the product side, we have 263 plus 4. That is 267 minus the mass of californium 249 gives you 18. By the way, the element which has atomic number 8 is oxygen. So this is oxygen 18. Again, if we analyze, this is not a particle, this is a nuclide. So we have two lighter nuclei that are combined to form a heavier nuclei. Okay, so this is a nuclear fusion. Okay, moving on for the next part for types of nuclear reaction. We are asked to fill in the blanks the following radioactive decay series. Okay, the particle above a arrow would indicate that is emitted by the nuclide head of it. So to determine the series that resulted from the emissions of this particle that is written above the arrow, okay, we have to refer to your periodic table. So thorium is element with a nuclide is atomic number. The atomic number of thorium is 90. If it's emit an alpha particle, we deduct 2 from the atomic number. So that is element 88 because plus 2. The charge is 2, 4. Then 200, element 88 by the way is the radium. Okay. So 232 minus 4, that is 228. Okay. Then after which, after emitting alpha, the radium will emit a beta. Again, the beta is negative 1 and a mass of 0. Okay, so the particle minus 1, you add 1 here, that is 89. Minus 1 is 88. Element 89 is actinium, Az. and there is no change in mass, 228. Then actinium will further emit, undergo another decay series of beta, -1, 0. Again, 89 plus 1, that is 90 thorium. Okay, 228 plus 0 is 228. Okay, for the second, we have uranium. And uranium from your periodic table is element 92, undergoing a beta decay. Uranium undergoing an alpha decay, 2, 4, a charge of 2, a mass of 4. So you have element 90 because 90 plus 2. Remember, that would be part of the product. Okay, that is 92. And element 90 is thorium. And 235 minus 4, that is 231. Then thorium 231 will undergo a beta decay, -1, 0. So that is element 91, because 91 minus 1 is 90. Element 91 is protactinium. And we add 231. Protactinium 231 will undergo further with alpha decay of 2, 4, a charge of 2, a mass of 4. So 91 minus 2, that is 89. And that is actinium. So 231 minus 4 is 227. Okay? Okay, for the last number, we have here protactinium is the product of an alpha decay. So, if an alpha decay produce a protactinium, so we can, and from the periodic table, protactinium is element 91. So 91 plus 2, it is 93. Element 93 is neptunium. Okay, neptunium, and we add 233 plus 4, that is 237. So the original nuclide is neptunium 237, undergoes alpha decay, producing protactinium 233. Okay? And the protactinium will undergo a beta decay. So we have 92. And element 92 is uranium. Okay, 233, because the mass of beta particle is 0. Okay, further, the uranium 233 will undergo an alpha decay. Therefore, we deduct 2 there. We have 90. Okay. And element 90 is thorium. And we have 229. Because 229 plus 4 is 233. Okay? So next, we are asked to balance the nuclear equation for the following reaction. Then you identify the X. So here we are given a transmutation notation. Again, recall the first symbol for the isotopes of the reactant, and what is written in the parentheses is the particle that bombard the reactant, or this is the particle the reactant side, and the second particle is the product particle. Okay, and the symbol after the parentheses is the symbol of the product isotope. Okay, so if you write the notation, if we have X plus proton will give you carbon 12 and an alpha 24, or we write it as helium. So to balance that, we have here 6 plus 2, 8, minus 1. So this must be 7. 7 plus 1 is 8. Then here we have 12 plus 4, 16. Minus 1, that is 15. So if you look in your periodic table, element that which has an atomic number 7 is nitrogen. So X is nitrogen 15. So to write that completely, we have nitrogen 15 when bombarded with a proton will produce carbon 12 and an alpha particle or an helium atom. That is another way of writing the alpha particle. The helium atom with a charge of 2 and a mass of 4. Okay. You may write this way or that way. That's the same. Okay, next, we have here aluminum 27 plus deuterium, hydrogen with a mass of 2 and a charge of 1 will produce X, an unknown, and an alpha or a helium for 2. That is another way of representing the alpha particle. So to determine the value of X, or to identify rather the X, we apply the technique that you have learned in balancing nuclear reaction. Okay, we balance the atomic number, that is balancing the charges from the reactant and the product, and we balance the mass number of the reactant must be equal to the mass number of the product. So here we have 13 plus 1, 14 minus 2, that is element 12. Okay, further, before we identify that, let us complete first the mass number. 27 plus 2, 29 minus 4, that is 25. Again, referring to your periodic table, the element with atomic number 12 is magnesium. So X is magnesium 25. So to write the complete reaction with the unknown X, we have aluminum 27 when bombarded by deuterium will produce magnesium 25 and an alpha particle. Okay, I just want to show you that we can interchange the symbol for helium atom and the alpha particle. Next, we have manganese 55 will give you X and a gamma, 0 charge, 0 mass. So therefore, if the charge of neutron is 0, gamma is 0, therefore it is 25, element 25. And we have 56 here, 55 plus 1, because the mass of neutron is 1, and gamma is 0. So we have 56 here. And element 25 is manganese. There's no change in atomic number. So this is an isotope of manganese 56. The isotopes of manganese 55 there both. So to complete that, we have manganese 55 when bombarded by a neutron. We'll have a isotopes of the manganese 56, 25, and a gamma particle. Okay. Next, we have selenium 80. So selenium 80 plus deuterium would give you X and a proton. You can represent the proton by the hydrogen nuclide. Okay, you have 34 plus 1, 35 minus 1. This is element 34, and that is selenium as well. 82 minus 1, that is 81. So the X is, again, the isotopes of selenium, 81. Okay, so selenium 80 when bombarded by deuterium would give the isotopes of selenium 81 and a proton. It's another way of representing a proton. Okay, here we have X plus deuterium would give you a product of lithium 9, 3, and 2 proton. Another way of writing the proton could be this way: a charge of 1 and a mass of 1, or the symbol for hydrogen atom. Okay, you have here 3 plus 2, 5, minus 1. So this has atomic number 4. We have 9 plus 11 because 2 times 1, 2 plus 9, 11. Minus 2 is also 9. So this is an isotone of lithium 9. And since we have element number 4 is beryllium, 49. So to complete the reaction, we have beryllium 9 plus a deuterium will give you a product of lithium 9, 3, and 2 proton particle. For the sixth number, we have here boron 10 plus a neutron will give you X, an unknown, and an alpha 24. Okay, you have 5 plus 0 is 5. If we minus 3, we have minus 2 rather, minus 2 is 3. So 3 plus 2, 5. For the mass number, we have 11 minus 4, we have 7. And element number 3 is lithium. You have 3, 7. So to write the nuclear equation, you have boron plus neutron. Boron 10 would give you lithium 7 and an alpha particle. Okay, let's have more example. Here we are asked to write the balanced nuclear equation for the following. Number 1, we have alpha decay of bismuth 188. So from your periodic table, you can determine the atomic number of bismuth, which is 83. You can write it here so you can balance the atomic charges later. Okay? So an alpha decay is emission from the nuclei. So the alpha is part of the product. Okay? So therefore, the reaction with the bismuth 188 will undergo an alpha 24. Okay? So 83 minus 2 is 81. Element 81 is thallium. Thallium. Okay, 188 minus 4, that is 184. So it is thallium 184 is the daughter nuclei when a bismuth undergo an alpha decay. Okay. Now next, if we have electron captured, okay, by lanthanum. Okay, lanthanum is 57. Okay. Now you may ask, why is it the atomic number is not written? Because the atomic number is unique to that nuclei. So you can consult your periodic table for the atomic number. But the mass number can change because we defined in the earlier discussion, isotopes are atoms of the same element with different mass number. And we have different types of nuclei. We have isobar, isotones. Okay. So what is written above or as the exponent is the mass number. The atomic number you can refer to your periodic table because that is a distinct or an intrinsic property of a nuclide. Okay? So we have electron captured here. So lanthanum captured an electron. So we have lanthanum 57 138 plus an electron which is -1 and a mass of 0. So when electron is captured, the product is element 56. And element 56 is barium. Okay, from your periodic table. Then the mass is the same. We have 138. Okay, we have balance. Now next we have beta decay. So when it decay, meaning it is the nucleus that emit that particle. So the nucleus of rubidium-87 emitted a beta particle. That is what you meant by that. Okay. So rubidium-87. So from your periodic table, rubidium is number 30. Atomic number is 37. Okay. It undergo beta decay. That means the beta is a product. So beta -1, 0. Okay. So to balance the charge from of the reactant and the product, we have 37 plus 1, that is 38, because 38 minus 1 is 37. And element 38 is strontium. Okay. And just copy the mass number of rubidium-87 because the mass of beta is 0. Okay, next we have niobium-89. Niobium is element number 41 here. Okay. It ejects a positron. So the word ejects meaning that is part the product. So niobium 89. When eject a positron is a positive one with a mass of 0. It's a positive beta particle. So that must be element 40. 40 plus 1 is 41. And element 40 is zirconium from your periodic table. Okay. So we just copy the mass number, okay, because the mass of a positive beta or a positron is also 0. Okay. Now, for the fifth number, we have production of thorium through beta decay. Okay. So, production of thorium 230 through beta decay. So that is negative 1, 0. Okay. The word production, that these are your product. Okay. So 90 minus 1 is 89. So element 89 is actinium. Okay, the mass is the same because beta particle has a mass of 0 and a charge of negative 1. So 230. So the mother nuclei is actinium-230. And this is the daughter nuclei, thorium-230, undergoing a beta decay. Okay, next is the formation of radium-220. Radium is element 88 from your periodic table. Here. Okay, next we have the radium is produced or formed through alpha decay. So we have radium 88, 220 is the mass. And that is produced through an alpha decay to 4. So we identify the mother nuclei. 88 plus 2, that is 90. And element 90 is thorium. And we have 224, 220 plus 4. So thorium will undergo an alpha decay producing radium-220. That's how you will write that statement. Next, we have formation of potassium Porti through positron emission. Again, the word formation, that means the potassium Porti is the product, and potassium has an atomic number of 19. And positron, that is a positive beta with a mass of 0 and a charge of positive 1. Therefore, we have here element 20. And element 20 from the periodic table is calcium. Okay. So 40 plus 0, you have 40 here. So calcium 40 undergoing a positron emission will produce a daughter nuclide of potassium 40. Okay, for the last number, we have technetium 94. From your periodic table, we have technetium is 43. Okay. The atomic number is 43. The formation of technetium through electron capture. So, an electron is captured and the product is technetium 94, which has atomic number of 43. Here, technetium 43. So to identify the mother nuclei, we have here, or the parent nuclei, we have here element 44, because 44 minus 1 is 43. And that is ruthenium. Ruthenium 44, and the mass is 0, 0, 0 for, no, that was 0 plus 94, that is 94. So the parent nuclide is ruthenium 94, capturing an electron or a K capture, which is the electron on the K energy level, the very first main energy level near the nucleus. The product is technetium 94. Okay, that is how we write a nuclear reaction and applying the technique that you have learned in the previous discussion on balancing nuclear reaction. Okay, the next topic would be on the determining the energy associated with this nuclear reaction, or the energetics. Okay, and the energy that holds the particle in the nuclide. Okay, see you then in the next episode on nuclear chemistry.